This is AP Calculus 2-9, the quotient rule. Today we're going to talk about how to use the quotient rule when you're taking the derivative. So you use the quotient rule in taking derivatives when you have a function over a function. So if your f of x has two functions within it, one over top of the other, this is the method you use to take the derivative. If we're going to let u and v be functions, and we're going to let f of x equal the functions u over v. So u is the numerator, v is the denominator. And then f prime of x, if you take the derivative of that quotient, this is what you would do. You would take the derivative of the top, the derivative of the numerator, times the original denominator, minus the original top numerator, times the derivative of the denominator, and that whole thing is over v squared, the denominator squared. Okay? Now, the most common mistake I see with this is students forget the v squared on the bottom. That's very, very important. So you need to train yourself to make sure you're doing that when you have the quotient rule. Now, this is very similar to the product rule. The product rule was the derivative of the first function times the original second function plus the original first times the derivative of the second with no denominator. In the quotient rule, we have the top derivative times the original bottom minus the original top times the derivative of the bottom over the bottom squared. Now, here's a way you can remember it. F prime, when you have a function over a function, is low d high minus high d low over low squared. So let's think about what that means. You're going to take the low function, the denominator, and multiply it by the derivative of the numerator. So that's low d high. Derivative of the high, derivative of the top times the original bottom. And then you're going to subtract from that the original top times the derivative of the bottom. Original top, derivative of the bottom. And that's all over the bottom squared. So low d high minus high d low over low squared would be a way to remember the quotient rule. So let's just do our first example here, and this is a fairly simple example. They don't get much easier than this one, but it's good to learn with the simple ones. If the simple ones work, so will the difficult ones. So same method for all of them. So we have an f of x equals 4x squared plus 2x minus 6 over 3x minus 5. So we have a function over a function. And if I look at that, the first thing I'm going to try to do is simplify it if I can. So if I can factor the top and then cancel something out, I'm going to try to do that. But hopefully your knowledge of algebra lets you know that, well, if I have, well, nothing goes into any of the coefficients right off the bat. So we can't take anything out without doing a little work. And then if we try to factor that top, 4 times 6 is 24, factors of 24 that subtract to give you 2. That would be 6 and 4, but if you think about that, if I were to factor that thing and try to cancel out the bottom, if I'm needing a 6 and a 4 when I factor, I'm going to have to break this 4 down into either 1 and 4 or 2 and 2. And so I'd have either 1x and 4x in the front of my binomials or 2x and 2x in the front of my binomials. And that tells me that they're not going to cancel out with the 3. So for this one, it's probably just easier to just do the formula and not worry about trying to simplify it. Now, you could take a 2 out of the top, but I don't think that's really going to help you here because you can't cancel it out with anything, and it might make it more confusing. So I would just leave it in there, take the derivative the way it is. So knowing that, if we take the derivative of this, well, it's low times derivative of high. So the derivative of the numerator is 8x plus 2. We're going to multiply that by the original denominator, 3x minus 5, minus high d low, the original high, which is 4x squared plus 2x minus 6 times the derivative of the bottom, 3. And then we can't forget that we have to take that bottom and square it. Not the derivative of the bottom, but just the original bottom. And then we're going to have to simplify this thing. So this is where our algebra comes in, and this is where a lot of students struggle with calculus because the algebra is a little difficult. So I'm going to FOIL this. That's 24x squared minus 40x plus 6x, so that's a minus 34x, minus 10. I'm going to distribute the minus and multiply the 3 at the same time. So negative 3 times 4x is minus 12x squared. That was an x squared. Negative 3 times 2 is negative 6x, and negative 3 times negative 6 is a positive 18, and that's all over 3x minus 5 squared. Then if I add my like terms, 24x squared minus 12x squared is 12x squared. Negative 34x minus 6x is negative 40x. Negative 10 plus 18 is positive 8. We have a 3x minus 5 squared. And then we should look at that and see, can that factor at all? Well, a 4 will come out. So I've got a 3x squared minus 10x plus 2. So we want to always simplify it if we can. And then 3 times 2 is 6. Are there factors of 6 that add to give you 10? And there are not. So that's as far as we could get. Now, if that would factor and cancel with the bottom, you would do that. You could factor out anything that will factor, but in this case, nothing does. So we have to leave it like that. So let's move on to some other functions here. We've got f of x equals natural log of 2x squared over e to the 2x. This, again, is quotient rule. So if I do f prime of x, I'm going to take the derivative of the top. The derivative of a natural log is the derivative over the original. So 2x squared, the derivative of that is 4x, and we put that over the original, 2x squared, times the original bottom, which would be e to the 2x, minus the original top, natural log of 2x squared, times the derivative of the bottom, that would be e to the 2x times 2. And then that's over the bottom squared. Now, if you think about that, e to the 2x squared. Well, isn't that, if you think about your algebra, if we square that, that's, we're going to take this and we're going to multiply it by all the powers on the inside. So isn't that going to be e to the 4x? Another way to think about that, e to the 2x times e to the 2x. We would keep the base and add the exponents. So that's another way to think of that if you're forgetting how to do the algebra. And so then if you look at this, we have a complex fraction here. We can't have a fraction within a fraction. So we're going to have to simplify some things. There are a whole bunch of different ways you could do this. I'm just going to show you what I think of first. You may think of something else first, and that's okay. It really doesn't matter how you simplify as long as we're getting the same answer at the end, okay? So a lot of people might look at this, the top and right here, and see that that's got a fraction, and they might want to get a common denominator right off the bat, and you can. But what I see here first is that every single term, this term has an e to the 2x, this term has an e to the 2x, and this term has an e to the 4x. So can I cancel out one of those e to the 2x's from every single term first? That's what I'm going to do first. So I'm going to distribute out that e to the 2x on top. Now if I do that, I have 4x, and actually, why don't I go ahead and simplify this fraction as well? The 4 over 2, that would be a 2 on top, and then the x on the bottom. So that cancels out. So that makes it a little simpler. I've taken out the e to the 2x here. So left inside, I have that 2. I'll put it in front. Natural log of 2x squared. And then that's still over e to the 4x, but I'm going to write it as e to the 2x times e to the 2x so that it's easy for you to see. That's what I'm canceling out. Now, you don't have to show that. You should know that you're going to subtract those and still end up with an e to the 2x, but just in case you need to see why that's working. And then on the top, we have 2 over x minus 2 natural log of 2x squared. And now that's all over e to the 2x. Well, I still need to simplify. I still have a complex fraction. Anytime you have a fraction within a fraction, you have to simplify that. So if you think about that, now, isn't it really easy to get a common denominator? Because really all I need is an extra x over here. So I'm going to put the x here. If I put it on the bottom, I also have to put it on top. And now I can combine those two things. So I would have a 2 minus 2x natural log of 2x squared over x. And then since this is on the bottom, can't I invert and multiply that and say that that's times 1 over e to the 2x? And when I do that, isn't this just going to become part of my denominator? So isn't this just going to be x times e to the 2x, allowing me to just get rid of that? And then if I look at that, if I can simplify anything, I would. Now I could take a 2 out of both terms, but there's nothing down here that would cancel with that. So if I think ahead a little bit, there's really nothing else I can do with that. I'm going to leave it like this. And then sometimes, this may be an application problem. They might ask you to, they might tell you that x is a certain number, find the slope of the tangent line at that x value. So there are a lot of applications we can do with this, but I wouldn't simplify it any further until you see what the application is that you have to use it for, and then determine what to do with it once you figure that out. They might say, tell us where the horizontal tangent lines are, you know, find the values of x where that's a horizontal, and you'd set it equal to 0. So I would wait to simplify any more than that till after I see what the application is that they're asking me to do, because that might determine how you simplify something. Sometimes when you do the quotient rule, you're going to have to rewrite the equation before you start taking the derivative. So if you have something like this, where you've got a complex fraction, you could rewrite this as x to the -1 and then do the derivative there and then the derivative here. But it might be easier if you just simplify this algebraically first and then do the derivative after you've done that, because then your function that you're dealing with isn't going to have a bunch of negatives, and it'll just be an easier function to get your information for. So I'm going to rewrite this. I'm going to make this a fraction, and then I'm going to simplify these two, put them together. So if I do that, I'm still going to write this f of x because I'm not taking the derivative yet. So I don't write f prime of x until I start taking the derivative. And so if I do this, this has an x, this needs an x. So if I make that denominator x, I also have to put an x on the top. So that would be 3x over x minus 1 over x. And then that's still over x plus 5. And then when I subtract that on top, I will have 3x minus 1 over x plus 5. Then I would invert and multiply. So that's really times 1 over x plus 5. So I can get rid of this. And so when I multiply those two together, I have 3x minus 1 over x squared plus 5x. And I think this is probably going to be a little bit easier to take the derivative of using the quotient rule. So I'm going to move this over here and then take the derivative. So if I take the derivative using the quotient rule, f prime of x, remember it's low d high minus high d low over the bottom squared. So the derivative of the top would be 3 times the original denominator minus the original top, 3x minus 1 times the derivative of the denominator over the bottom squared. And then I would simplify this. So I'm going to distribute the 3, foil this, and when I foil, I'm also going to distribute a minus sign. So when I foil that, I have 6x squared minus 2x plus 15x will be plus 13x minus 5. And then if I distribute the minus sign, this will be a minus 6x squared minus 13x plus 5. And then that's all over the x squared plus 5x squared. And then I add like terms. So I'd have negative 3x squared plus 2x plus 5 all over x squared plus 5x squared. So there's my derivative using the quotient rule. Next I'm going to do a couple applications of the quotient rule. In this function here, they give you that f of x equals tangent x, and they want you to find the equation for the tangent line when x equals pi over 3. So if you're trying to find the equation of the tangent line, remember you need the ordered pair and you need the slope that goes along with that ordered pair at a specific x value on your function. So I could go ahead and plug pi over 3 into the function. So if I want to find f of pi over 3, I just do a little bit of trig. So I'll draw a little unit circle up here. Now pi over 3 is 60 degrees, and I know at 60 degrees that ordered pair would be 1/2 square root of 3 over 2. So tangent at pi over 3 is going to be sine over cosine, which is square root of 3 over 2 over 1/2. And if I invert and multiply, the 2's are going to cancel out, leaving me with square root of 3. So the ordered pair at pi over 3 for the function f of x equals tangent x is the ordered pair pi over 3 square root of 3. So the x value is pi over 3, and the y value is square root of 3. Now, in order to find the equation for the tangent line, all we have to do is find the slope of the tangent line at x equals pi over 3. Now, how do we find the slope of the tangent line? Well, we learned earlier that the slope of the tangent line is the derivative of the function at a specific point. And so we would find the derivative of f of x equals tangent x, and then plug pi over 3 into what we get, and that will be the slope of the tangent line at that point, pi over 3. So now, this is a problem because we don't know how to take the derivative of tangent. There's no way to do that. We've only learned how to do sine and cosine. So there must be a way to find the derivative of tangent. So if you use your trig identities, you know that tangent is the same thing as sine x over cosine x. So if we know that tangent is sine x over cosine x, we can rewrite it as sine x over cosine x, and then we can take the derivative of that using the quotient rule. So here's another reason we need the quotient rule, to be able to figure out what the derivative of tangent is. And you're going to learn the derivative of the rest of the trig functions soon in this chapter. But this is a good way to kind of derive what the derivative of tangent x is, to use it in an application. So that's what we're going to do. If we take the derivative of that, f prime of x, well, that's low d high minus high d low over the bottom squared. So low d high, the derivative of the top, derivative of sine is cosine x, times the original bottom, cosine x, minus the original top, sine x, times the derivative of the bottom. The bottom is cosine x. Derivative of cosine x, remember, we said was negative sine x. So we're going to put a negative sine x. And if it's negative, that's going to change that to a plus. And then that's over the bottom squared, cosine squared x. And so then, if you notice, you've got cosine x times cosine x plus sine x times sine x. So f prime of x is equal to cosine squared x plus sine squared x over cosine squared x. Okay? And then when you do this, you need to recognize this as one of your trig identities. Remember, cosine squared x plus sine squared x is equal to 1. Cosine squared x plus sine squared x is equal to 1. Trig identity. It's one of the real basic trig identities. So if we can recognize that is 1, then look at what we have here. F prime of x equals 1 over cosine squared x. 1 over cosine squared x, there's another trig function or trig identity. Remember, 1 over cosine squared is secant squared. So the derivative of tangent x is secant squared x. So we've found, or we've derived the formula for the derivative of tangent using the quotient rule. Okay, so the derivative of tangent is secant squared x. Now, to go a little bit further, remember the directions were to find the equation of the tangent line. Well, we found the ordered pair. Now we need to find the slope of the tangent line. To do that, we're going to take f prime of x equals secant squared x, and we're going to find f prime of pi over 3. Well, if f prime is secant squared x, then we're going to find secant squared of pi over 3. So we're going to go back to our unit circle. Secant, remember, is the inverse of the cosine function. So secant at pi over 3 is going to be the inverse of cosine at pi over 3. Well, cosine at pi over 3 was 1/2. The inverse of that is 2. So secant at pi over 3 is 2. We have secant squared, so that's 2 squared. So f prime at pi over 3 is going to be equal to 4. So that means my slope, that's the slope of the tangent line. Remember, slope is the same thing as the derivative. Okay, the slope of the tangent line is the derivative. It's a rate of change. There are a bunch of different ways to say it. It's a velocity, if we were talking about speed or movement. So the slope here is 4. The ordered pair we're going to plug in for is pi over 3 square root of 3. And all they said here was to find an equation. Well, what's the easiest equation from algebra to plug all this information in? The one that you can plug a point and the slope into. So point slope form. Remember, point slope form is y minus y1 equals m times x minus x1. And this is a reason we should never skip that in algebra 1. Y minus square root of 3 equals m, which is 4, times x minus pi over 3, and here is the equation of a tangent line. It did not say it has to be in slope-intercept form. It didn't say it has to be in any certain form. So we have accomplished what they've asked us to do. You never want to go further than what they ask you to do in calculus because it wastes time, and sometimes the work can be very difficult to get what you think you need. So all they ask for is an equation. We've got an equation. We stop here. We don't go any further than this. Save time. Okay? Remember, if you have to take the AP test, it's a time test. So anywhere we can save time, we want to. All right, the next application. This is the next application of the quotient rule. Here, I have two functions that are graphed. They're piecewise functions, but that doesn't really matter. This is f of x on the top here, and g of x is here. And they're telling us that h of x is equal to f of x over g of x. And down here, they're telling us to find h prime of 3. Well, if h of x is f of x over g of x, in order to find h prime of x, wouldn't we have to use the quotient rule? So that's the first thing I'm going to do. I'm going to find h prime of x. So I'm going to do that right here, h prime of x. Well, h prime of x, since that's a quotient, is going to be low d high minus high d low over the low squared. So the derivative of the top is f prime of x times the original bottom minus the original top times the derivative of the bottom all over the bottom squared. So there's the derivative of h prime of x, and what they've asked us to do is find h prime of 3. So what I'm going to do here is every x that I have, I'm going to plug 3 in for it. So h prime of 3 is f prime of 3 times g of 3 minus f of 3 times g prime of 3 over g of 3 squared. Now, how am I going to plug into this information? Well, I'm going to look at my graph. Remember, f prime of 3 would be the slope of the line at 3. So if I'm looking for f prime of 3, I'm going to go to the f function, I'm going to go to 3, I'm going to look at where it is, and I'm going to look at this and I'm going to say, what is the slope of that line going through 3? Well, it looks like it's 1 over negative 3, or negative 1/3. So h prime of 3 is going to be negative 1/3 times g of 3. Okay, I go to 3. G of 3 is what the ordered pair is, or the y value of the ordered pair at 3 of the g function. So I go to the g function. The ordered pair at 3 is 3, negative 2, so the y value there is negative 2. So g of 3 is negative 2 minus f of 3, the f function, the x value is 3, f of 3 is 4. That's the y value at f of 3. So that's 4. G prime of 3 is the slope of the g function at the point 3. Looks like negative 1, 2. That's negative 1/2. And that's all over g of 3 squared. Well, remember we said g of 3 was negative 2. So that's negative 2 squared. So then, if I look at what I've got, negative 1/3 times negative 2, that is 2/3. 4 times negative 1/2 is negative 2, so a minus negative 2 would be a plus 2. And that's over 4. So 2 plus 2/3. Well, that's 2 2/3, which would be 8/3. I'm going to move over here. So we've got 8/3 over 4. Well, I invert and multiply. That's 8/3 times 1/4. The 8 and the 4 cancel, leaving me with 2/3. So h prime of 3 is going to be 2/3. So you get a pretty simple answer for something that seems complicated at first, but if you really think about what they're asking you to do here, none of this is that difficult. You're just putting some information together.